1, 2, 3. Okay, so sorry for the delay and welcome to this session about reactive streams and Java 9. My name is Jacek Kunicki. I work at Software Mill. We are a software consultancy. We write code like most of you do, probably. There are two special things about us, however. First of all is that we are a fully remote company, so we don't have an office. The second one is that we have a completely flat and transparent structure, including the financial stuff. So if you are eager to hear more about how this works or how it doesn't work, please feel free to catch me after the talk. And now let's get back to the merits of this talk, so reactive streams. Let's start with a quick recap what stream processing is and what reactive stream processing is actually. So I think most of you are rather familiar with the typical architecture of stream processing. So basically you start with some source of your data, which you can call a producer. Then you have a destination for your data, which you can call a consumer. And you have a number of processing stages in the middle, which do something with your data. And then, of course, you have data flowing from the producer through the stages to the consumer. So this is like a general stream processing pipeline. And if you think about it, and if you think in terms of different speeds of the producers and consumers, you may get to a conclusion that there can be some troubles when the producers, generally when the producer is faster than the consumer. Because then there is some excess data with which the consumer has to deal somehow. And there are, of course, a number of approaches to dealing with that excess data. For example, the simplest approach is basically to drop the data. So this is actually something that happens on the hardware level in some of the networking hardware. Basically, when there is some data that the slower consumer is not able to handle, it's just dropped. Of course, this is not an ideal solution because you are losing data. Then, for example, you can buffer the data. So the consumer, either the producer can buffer the data that it's sending to the consumer, or the consumer can buffer the data and then process it. But if the producer is really fast and the consumer is really slow, so the buffer grows, and buffers, as we know, have limited capacity. So there comes a point in time when the buffer overflows and something wrong happens with your application. Another solution to deal with this excess data is to block. So for example, the consumer can just consume and process the data as fast as it can, but if it's not able to accept any more data, it's just not going to accept it. So it's basically going to block the producer. There is, however, another way, which basically leads us more towards reactive streams. This way is called backpressure. Backpressure is basically a way for a slower consumer to signal demand to the producer. So we introduce something like a separate channel for communication between the consumer and the producer. And with backpressure, it is the consumer that tells the producer how much data is going to accept. So backpressure is basically data flowing, you can say, in the opposite direction than the actual data. Every reactive streams implementation, because there are a lot of them, can have its own naming for the building blocks here. So in reactive streams in Java, the producer is called the publisher, the consumer is called the subscriber, and the intermediate stages are called processors. So far, this is a stream processing pipeline with backpressure, but it's not yet reactive. So let's now see what would make this pipeline with data and with backpressure reactive. So there's a couple of crucial things. First of all, it needs to be asynchronous. So the data needs to be sent in an asynchronous fashion, not to block, basically. And then, which is, I think, the most crucial thing about reactive streams, is that the backpressure itself is not blocking. Because if the backpressure was blocking, it could still not make the entire pipeline fast. The aim of being non-blocking and for being asynchronous is basically to reuse the CPU resources or the threads as often as possible. So whenever you don't need a resource, you're just giving it back to the CPU, and then other threads can use it, basically. So this is the most crucial thing, that the backpressure is non-blocking. Now, the other important thing about reactive streams is that the slow consumers, so the fact that the consumer can be slower and may not be able to cope with lots of data, this is somehow represented in the domain model. So normally in a traditional stream processing pipeline, you don't have any notion of the fact that the subscriber can be slow. But here in reactive streams, you try to represent it somehow in the domain model. And I have two examples for that. First one is the Twitter API. So if you use the Twitter API, and actually Twitter is allocating like a connection for you, and then it is sending you data, but it is also monitoring how fast you are consuming the data. And if it notices that you are consuming too slow, it can send you a special message which says that, hey, you are consuming too slow. If you don't speed up, we're going to disconnect. So this is a way that, apart from the actual data that is being sent to the client, we also have some special informations, which is the domain representation of the fact that something can be slow, to the consumer, and then the consumer needs to react. Another example comes from Akka Streams, which is one of the implementations of Reactive Streams. And in Akka Streams, we have a stage, so the intermediate block in the pipeline, the processor, that is called conflate. And what conflate basically does, it observes the consumer, and if it notices that the consumer is slow, it starts aggregating data. And only when the consumer becomes quick enough, again, it starts sending the data in bundles that it has aggregated. So this is another example of how we represent a slow consumer in the APIs or in our domain model. So now starting from Java 9, now we already have Java 11, it's changing quickly, but starting from Java 9, the java.util.concurrent.Flow class appeared in the JDK, and it contains a number of interfaces that represent reactive stream processing. Actually, you may have seen it earlier in the org Reactive Streams packages, but then they were separate from the JDK, and only starting from JDK 9, they became a part of the JDK itself. So let's now have a quick look at the interfaces, so what JDK offers us in terms of reactive processing. The first interface is called the publisher. It's pretty straightforward because it just produces elements of some given type which the subscribers are going to consume. And it exposes a method for a subscriber to register. This method is called subscribe. And then the subscriber says that, hey, I want to connect, I want to receive data. Then comes the subscriber, which, well, as I said, subscribes to the publisher in order to receive some data. And then it can receive a couple of callbacks. So it exposes 4 methods that can be used. First one is onSubscribe, which is basically a confirmation that the connection has been made. Then it can receive some data with the onNext method. It can receive errors via onError. And eventually, when the pipeline is complete, it can receive a completion signal. Now here you can notice something called the subscription. Subscription is the next interface, which basically represents a link between a publisher and a subscriber. So we have a data type that represents that those two are connected and will be sending data. And subscription exposes 2 methods to control how the data flows. First one, and the most important one in terms of reactive streams, is called request. And this is the place which is actually responsible for the backpressure, because this is the way for the subscriber to tell the publisher how much data it wants, basically the number of elements that I'm going to accept next. And there is also a cancel method, which allows to cancel the connection between the subscriber and the publisher. There is also a processor interface, which is basically a combination of a subscriber and the publisher. So if you want to implement a building block inside your pipeline, it needs to have an input and an output. And this is basically how it combines the publisher and the subscriber. And it's called the processor. So once again, to recap, the typical scenario is that a subscriber is connected to a publisher with the subscribe method, and then it receives the confirmation signal, the onSubscribe. Then it can receive an arbitrary number of onNext signals with data, and eventually it completes either successfully or with an error. So now we are developers, and when we see interfaces like that, they are pretty simple. It's really tempting to try to implement them ourselves. So let's try to do it. What we would try to do now is to implement a simple publisher. That is, it is going to hold an iterator of integers, and it's going to accept subscribers and then emit the data to subscribers. So since we implement the publisher interface, it exposes a single method that we need to implement, to write code ourselves, which is called subscribe. So the very naive approach to this problem would be to just take the iterator and say that for each remaining element, we want to call onNext on the subscriber, so send data to a subscriber. And then after the iterator has been exhausted, we want to complete the subscriber. OnComplete. So this is our very naive implementation. Let's try to run it and see if it has a chance to work at all. So we need a main method with new simple publisher. Let's say we want to send 10 elements. And then we need to call subscribe and provide a subscriber or a consumer to do something with the data that the publisher is going to send. So let's choose an anonymous implementation of a subscriber. And let's just implement two methods here, the onNext and onComplete, so that we can see the elements that are actually processed and then the completion. So in onNext, we're just going to print the item we received, so the parameter. And in onComplete, we're just going to write that we've been completed. Let's now try to run it and see what happens. So, well, it looks like it worked. All the elements have been emitted, they have been processed, the pipeline has been terminated. So we could think that this is a good way of implementing a publisher, but it's not. So you may notice that, for example, the crucial thing that we don't have here is the backpressure. So the backpressure was represented by the subscription. What was included in the subscription? We had the request method to request more elements, and it's not there. And actually what we are doing here is when subscribe is called, we're taking all the elements, sending them, and there is really nothing about requesting data and only sending as much data as requested. So this is certainly not a correct implementation of a publisher. And we have a way to prove it. To prove it, we are going to use something that is called a Reactive Streams TCK, or Technology Compatibility Kit, which is basically a number of tests that you can run against your implementation of the Reactive Streams components. And what the TCK checks is how your components are going to interact with other proper Reactive Streams implementations. So whether they are going to behave correctly in terms of all the signaling, in terms of backpressure. So we have here a test for our simple publisher that uses the Flow publisher verification, which is a class from the Reactive Streams TCK, and it basically creates a new instance of our publisher and is going to test it. So let's now run the test from the TCK against our implementation, and it won't be a surprise that we prove that it's not correct. Yeah, so you can see that, well, we have 15 tests. They have failed. One of them is still running, but it also signals that something is wrong here. So this is not the best result because only a single test has succeeded. And it's actually, well, it's no surprise that it succeeded because it expects a null pointer exception and null subscriber. We are doing something with the subscriber, so if it's null, a null pointer exception is thrown. So now we have a proof that our implementation was not correct, which is not a surprise because it was really naive and simple. So let's now try to fix it and to see what we can do to make the implementation adhere to all the requirements of the TCK. Let's start with the first requirement, the failed one, that we need to issue onSubscribe when a subscriber, a non-null subscriber, is connected. By the way, the numbers here are the numbers of the requirements in the Reactive Streams TCK, so in the specification, so that it's easier to navigate if you go to GitHub and read the requirements. So what we want to do now is to actually call an onSubscribe on the subscriber when the subscriber is non-null. So I'm going to fold the main because we're not going to need it. Let's delete this code because we know it's bad. And what we are going to start with is the onSubscribe. So now we have our subscriber, we're calling onSubscribe. Well, when the subscriber is null, a null pointer exception will still be thrown, so we're going to satisfy that requirement. And now you can see that it requires a subscription. So this makes sense because subscription is the link between the publisher and the subscriber that we want to establish. So it looks like we need to implement subscription ourselves as well. So let's call it simple subscription. And then what we are doing now is basically moving the logic of sending the data into the subscription. So to be able to send the data to the subscriber, we need to have an instance of the subscriber in our subscription. That's why we are going to pass it here as an argument. And let's create it as an inner class here. We're going to store the subscriber in a field. And now we have a two methods actually to implement, as you may remember. First one is request, which deals with backpressure and with sending as much data as requested, and the other one is cancel. So now the first thing that we need to do in request, well, we need to respond to this request. So we have n elements requested, and we need to take n elements from our iterator and send them to the subscriber. So this sounds pretty simple, so we can just write a for loop. Let's call the variable demand. It starts with n. We need it to be greater than 0. And also, in order to emit anything, we must ensure that the iterator is not empty. So we also need a condition on the iterator here. Has next. Now we're decreasing the demand. And this is our for loop. And what we are doing here is pretty simple. So we're just saying subscriber on next and sending the next element from the iterator. Also, when we send the requested n elements, or at most n elements downstream, we want to check whether the iterator hasn't been exhausted, because if it has been, we need to terminate the pipeline, so we need to call cancel. Sorry, not cancel, but onComplete. So what we do here is we check whether the iterator is empty, so not iterator has next. And if the iterator is empty, we call subscriber onComplete. And that's pretty much it. So let's run the tests, the TCK tests once again, and see what happens. So we've been fixing 109, and it looks like we succeeded. So this test is green. There are a lot of others that are not green yet, but we'll try to make them green in the next steps. So we fixed 109. Let's look for something else to fix, probably something simple. For example, if you have a look at 309, there are two requirements. And basically, they say that if zero elements are requested or a negative number of elements is requested, we need to signal an error because we're not going to handle it. Well, that also sounds pretty easy to implement. So let's just add an if here. And basically, we're going to we can cover them with a single if, because we basically check if n is less or equal to 0. And then we would be tempted to throw an exception. But we need to remember that we are actually not allowed to throw an exception here, because that doesn't adhere to the specification. Actually, what we want to do here is use the onError callback on the subscriber to pass the exception that we would throw otherwise. And it expects an illegal argument exception. And running the test once again, we can see that both 309s were fixed. So we have correctly handled the case where 0 or a negative number of elements is requested. Now if we look at some other issues here, we can notice 105 and 107. And if you look at the errors, they are pretty much similar, at least the exception here, because it says that an unexpected additional complete signal was received. So it basically means that we are signaling completion too many times. Maybe because of the fact that this is executed in a couple of threads, and there are some race conditions, and we are doing more than once, and the expected behavior is to signal it only once. So this suggests that we need some state in our subscription to hold the information about the termination of the pipeline. Let's try to introduce it. So what we are going to use is an atomic Boolean as a flag to basically hold the information whether we have been terminated or not. It's going to be called terminated. And we start with false because initially the pipeline is not terminated, of course. And now, of course, the field is not enough. We need to use it somewhere. The most obvious place to use it will be the cancel method, because if the cancel callback is received, we need to set the terminated flag to true. Now there are two other places where we need to use it. The first one is here before emitting something downstream, because apart from checking that the iterator is not empty, we also need to check whether we have not been terminated, because if we have been terminated, we're not allowed to send anything downstream. So we need an additional condition here that terminated is false. And the other place where we need to use it is here before signaling completion, because actually the error we got was that completion was signaled too many times. So before signaling completion, before using the onComplete callback on the subscriber, we also need to check whether we haven't been terminated. And here is the place where we should actually flip the flag, because if we are signaling completion, we need to set the flag to true. But this has a problem. The problem is that this is not atomic, so we are checking the flag and then setting it, but this is not an atomic operation, which may get us into trouble still. But actually, atomic Boolean has a method that can take the value and then set it in an atomic way, and we are going to use it. So we are not calling terminate set here, but we will be using terminate get and set to true. And what it does, it takes the value, which is going to be used in the comparison in the if statement, and then it is going to set it to true so that we know that we are terminated. And this is going to be an atomic operation, which is expected here. So when we run the test once again, you can see that it's much better. There are only 2 failed ones. But actually, this is the place where I'm going to stop trying to implement it, because if you look at the errors that we have here, they are not that trivial. So the errors we had previously were pretty easy to fix, because we just needed to add an if statement, we needed to add some flag, an atomic one, but this is still a flag. But here we have 2 problems. First one of them is an unbounded recursion. And the second one is dealing with large values, the large number of requested elements, where large means long max value, for example. So here you can see that we got a Stack Overflow error, which actually this is caused by the fact that our implementation is synchronous and that we actually allow unbounded recursion. So this caused the Stack Overflow. And here in the test case specific for unbounded recursion, we can see that it also fails. So that there is a problem with unbounded recursion here. So let's try to focus on those 2 errors a little bit more. So the unbounded recursion is basically caused by the fact that, first of all, our implementation is synchronous. And then in our request method, we are calling onNext on the subscriber. And then, like the typical behavior of a subscriber, when it receives the onNext callback, is to process the element and then request next elements. So we are getting into a loop where request on next requests are called infinitely. This is a problem in a synchronous implementation. But then if you would try to switch to an asynchronous one, we would get into some other problems, which is handling infinite demand. Infinite meaning long max value, for example. Because if you imagine a multi-threaded environment, and then if you call request with long max value, and then if you try to allocate, for example, max value like long max value threads, then certainly you are going to run out of them. Even if you try to allocate a bit less, you can still run out of the threads. And if you try to approach the problem from another side, for example, try to store the demand somewhere and then use it in a smarter way, you can get into long overflow. So this is still not going to work. So those problems suggest that actually implementing even a publisher yourself isn't that simple. And actually, publisher is in the middle of the scale of complexity when it comes to implementing it yourself. Like the simplest part to implement would be a subscriber. Then comes the publisher, and the most difficult part would be a processor. So publisher is somewhere in the middle. And basically, the bottom line of this demo here is that you shouldn't really be doing this yourself. Unless you know what you're doing, of course, unless you're implementing your own reactive library, and if you are using the TCK and adhering to the TCK, it's okay. But just implementing the interfaces in a very straightforward and naive way may cause your library to break something else. So when writing this yourself, you really need to at least look at the TCK, run the TCK, and make sure that it works with the TCK. So if we are not, if we shouldn't be implementing the interfaces ourselves, the question is, what are they in the JDK for? And the answer is they are serving as something called an SPI, or a service provider interface, which is basically a layer to integrate different implementations. So then you may imagine having a number of Reactive Streams implementations, and the Java concurrent Flow interfaces are there to enable you to integrate those different implementations together. So now if you look at the streaming abstractions or abstractions close to streaming that we have in the JDK already, there is a number of them. For example, you may start with something that even has a stream in the name, so file input and output streams, which, well, it is clear that they resemble a streaming behavior. But for example, if you want to transfer data from one file to another using input and output streams, you need to do all the logic yourself. You don't have the backpressure included, so there is a lot of manual work. There are, for example, iterators, which basically are about handling infinite streams of data, which streaming is also about. There are file channels in the new I/O. There are even read and write listeners in the servlet API, which also expose quite a bit of a streaming behavior. There is Java SQL result set, which is usually backed by a cursor in the database. So this is a bit similar to an iterator, which is still, again, about handling an infinite stream of data. There are, of course, Java streams that came with Java 8. And there is java.util.concurrent.Flow that came with Java 9. So there is a number of abstractions here, but they are not unified. So what we actually would like to have here is a unified way to connect those elements together. So with this simple subscribe method, well, it looks simple, but if you think of it carefully, it hides all the complex behavior inside. It covers backpressure, which is the crucial part of reactive streams processing. It covers error handling, signaling completion, and all the complex stuff that we have inside. And we are actually missing it. So we have a number of abstractions that I've just shown, but no unified way to connect them. So now let's try to turn towards an ideal world and see what it would be nice to have in the JDK. And the disclaimer is that there are things that are not in the JDK. We're not sure whether they would ever be there, but it would be nice to have them to be able to use all these streaming pieces in a unified way. So first of all, what the JDK is lacking is a minimum operation set for the streams themselves. So we only have interfaces. We have the publisher, subscriber, subscription that connects those two. There is actually a single implementation that is called submission publisher, and you could use it, but it's not the best performing one. So using it for some more complex stuff may be a good idea, but using it for some simple operations like filter or map on your data is really not the best choice. So we can still say that we are actually missing this basic operations, because this is something that you usually do. If you used any Reactive Streams implementation like Akka Streams or RxJava or Project Reactor, those things are there. So there are some basic operations that you would normally do on a stream. There is actually an initiative by Lightband called Reactive Streams Utils, and this is a library that provides the basic operations, but then allows you to plug in the implementations of all the more complex operations by just specifying a system parameter to your program. So this is this would unify things a bit, because this would give you the basic operations, and then if you want to use Akka Streams for the more complex stuff, or you want to use Project Reactor, you are free to choose. But there is still a bit of politics around it. So we have, on the one hand, we have Spring with Project Reactor, and Spring is really not interested in doing reactive streams in any other way than using Project Reactor, because Project Reactor is like heavily built into Spring, and all the reactive stuff in Spring is done with Project Reactor. On the other hand, we have Jakarta EE, so the new Java EE, which is which could be interested by having things inside the JDK. And there are still a lot of companies who are using Java EE or Jakarta EE, and they would really like to have things inside the JDK or inside Java EE, so they don't have to use Spring. So there is like still a bit of politics here, and it is not unified. The next area that I would like to look at in terms of what it would be nice to have in the JDK is HTTP. So when it comes to HTTP, we have async servlet I/O from servlet specs 3.1. Then starting from JDK 9, we have the new HTTP client. And actually, it was in JDK 9 and 10, it was in the JDK incubating package, so it was not considered stable. But starting from JDK 11, it has become a part of the java.net.http. So it's now official. It's now inside the JDK. And this is an HTTP client that has a nice API, much better than the HTTP URL connection. And it also exposes some of the reactive behavior. So it uses the reactive interfaces, and for example, it provides a post method that takes a publisher, with which you are able to support data to your post method. And then if we imagine that HTTP servlet request provided a body publisher, it does not, but if it did, if you think of file upload, then it would become a really simple thing, because then you would just call post with the publisher supported by the HTTP servlet request. Well, at the moment it does not support it, so it's not doable in such a simple way. But it would be nice to have something like that, because then you would have like a reactive file upload with backpressure, with all the signaling inside, with just a single call like that. Another area of interest, and that is, I think, used pretty commonly, is database access. So when it comes to database access, actually Oracle tried to implement a reactive approach in the JDK. This is called ADBA, or Asynchronous Database Access API. But it turned out that, well, they hit the wall basically, because they were not able to implement all the reactive parts so that they adhere to the TCK, and they dropped support for reactive. So there are still some works around ADBA, but it's pretty sure at the moment that they are not going to support the reactive interfaces. There is another thing about which I actually learned half an hour before my talk, which is called R2Dbc Spi. This is like another approach to try to implement a fully reactive database access layer with an SPI, so with exposing all the reactive interfaces. And it actually connects with Spring Data. So if you are using Spring Data with all the annotations and all the automated generation of methods to access your data, this would work with that. Apart from the fact that this is still experimental. So I spoke to Oleg Dokuka, who played a bit with R2Dbc, and it turns out that there are still a lot of errors. So the intentions are very good, but there is still a lot of work to do. So we still can't think of anything stable that is going to support reactive database access. There are some existing drivers that are vendor specific. So well, they can be there, but there is not a unified layer above them. Now, if you imagine what JPA could look like if you had the reactive behavior inside, you could imagine like a query that you normally do, which here you have a publisher of users, but normally you have a list of users here, and instead of getResultPublisher, you have getResultList. So the approach with list and getResultList is not reactive, and if JPA was able to return a publisher, then you would be able to communicate with your database in a reactive way as well. But this, once again, is something that you could, well, dream of. It's not there yet. There are, of course, some more things that you could expect to be in the JDK, which would make your lives easier. For example, Reactive File I. So if you had something like a publisher of byte, then you would be able to, coming back to the example of transferring data from one file to another in the reactive way, if you had a publisher and a subscriber of byte, then you would just call subscribe to connect those two, and then it would just go to work in a reactive way. You can think of JMS, which is also about, well, it's not really about streaming, but it's about sending messages in an asynchronous way. So we could really use some reactive interfaces here as well. We can think of WebSockets, which is also, again, about streaming data, and we might think of use cases where you would want to be able to control backpressure and different speeds of the parts in the pipeline. If you think of AWS, for example, actually it turns out that AWS is trying to implement the reactive approach inside their libraries, but it's not going to be exposed. So they are doing reactive stuff internally, but the APIs that they are exposing are not reactive, and probably they won't be. So this is not ideal as well. Then we have Project Alpaca. If you haven't heard of that, it's basically a set of connectors for Akka Streams. Akka Streams is one of the implementations of Reactive Streams, and Alpaca is something that you can think of as Camel. So Camel is a layer of is basically aimed for integrating different data sources and destinations. And Alpaca is a set of connectors that try to resemble the Camel connectors to different data sources and to basically different things, so that you can bind the sources and destinations together in a reactive way. But still, Alpaca is not a part of the JDK. It's an external library, and what we are trying to cover here is our expectations for an ideal JDK and for an ideal reactive support in the JDK. So now, since there are not too many things to show how that can be integrated from like different libraries, but I still want to show you how what the SPI is aimed to be, which means a layer of integration for different implementations. I want to show you how we can connect to not simple, but to simply connect through 3 implementations of reactive streams. So we're going to take a source of our data from Project Reactor. This is going to be a Flux. Then we want to use Akka streams as the processor, so doing something with our data. And then we want to take RxJava as a subscriber for our data. So this demo is going to show that actually using the interfaces from the JDK, we are able to use different implementations. And in the future, if we had some more complex stuff implemented in a way that adheres to those interfaces, we would be able to connect them in a similar fashion. So when we go to the integration demo, so you can see that, well, we're starting with a Reactor publisher. I'm going to show you the implementations later. Now let's just see what the pipeline looks like in general. Then we have a processor that comes from Akka streams. Then we connect those two with subscribe. And then we take a Flowable, which is from RxJava. And then what we do is we use it basically to connect to the processor as the output. So what we are doing is taking data from the publisher, from the Reactor publisher, processing it with Akka streams, and then sending it to the subscribe method from RxJava, the one here, and supplying a function to just print it to standard output. So if you look at the signatures of the methods here, you can see that those are actually the java.util.concurrent.Flow interfaces. So we're actually using the SPI here. But inside, they are specific to the implementations. So here for the Reactor publisher, we are actually creating a Flux using the interval method, which basically generates values in an interval of 1 second in this case. And then we need to use some glue code that is actually going to convert the Flux to the Reactive Streams interface. So here is where the conversion takes place. And this is pretty similar in Akka streams. So here we create a flow, which is Akka streams terminology for the processor, so for the building block in the middle. We have some logic in the flow, which is negating values in our case. And then once again, we're using some glue code to convert the flow type to the java.util.concurrent.Flow processor here. Now what you can spot here as well are some differences in how the reactive streams implementations are done. So you can see some, if you haven't used Akka streams before, there are maybe some mysterious stuff like an actor system and a materializer. And this is basically how you specify a runtime for the Akka streams graph. So Akka streams approach separates the definition of the pipeline from the runtime. So you build a definition, then you define a runtime, and then you need to be explicit about it. On the other hand, and on the contrary, in Project Reactor, you actually don't really deal with the runtime. You just specify what you want to do, and you don't need to be explicit about how it's going to work under the hood. So this was for the explanation, and now let's just try to run it. Yeah, so 0 is not negated, but then you can see that the next elements are actually negated. So this works, and this shows how we can connect different implementations of the same interfaces together, and this is still going to work. So once again, basically, if we had some other things implemented in a reactive way, like HTTP or database access, we should be able to combine them in a similar fashion, like here. So to sum up this talk, the important thing to remember is that what we have in the JDK is not a full reactive streams implementation. So it's actually only a set of interfaces that are meant to be used as an SPI, so basically as an integration layer for different implementations. So it's a unified way to connect different reactive implementations. And as you saw in the initial demo, implementing them yourself is really not trivial. So there's a lot of things you need to think about, which are not obvious at the beginning. So just going naive way may appear to work, but then if you connected it to a true implementation of Reactive Streams, there can be some problems there. So if you are planning to actually implement the interfaces yourself, you need to use the TCK, because the TCK is the standard. This is the set of tests that somehow guarantees that your implementation is going to behave correctly with all the other implementations of Reactive Streams. There are some resources if you're interested. So the first one is the pluggable runtime, so the Reactive Streams Utils. Once again, this is the basic set of operations that you can then extend by your implementation of your choice of the Reactive Streams. This is the TCK, and actually TCK is not only the set of tests, but this is also an extensive documentation. So all the requirements that you could notice in our test case are described in detail. There is like background, why is it important, what behavior does it expect. So if you are going to do it yourself, it's really a good starting point to read it and to understand it. There is a blog post about ADBA, which describes it, but as I said, probably it's not going to be used as a reactive implementation, so this is just like out of curiosity. And there is a really nice series of blog posts called Advanced Reactive Java, so which covers much more that I showed here while trying to implement the publisher myself. So this is really worth reading, and please also have a look at it if you want to try implementing the reactive parts yourself. So that's all I had for today. Thank you for your attention. If you have any questions, I'm happy to answer them now or later. And I got this slide to include, so I will be really grateful if you rate my talk in the inventory app, especially if you get some negative feedback that you didn't like something. Please come to either say it to me directly or post it in the app. I will be more than happy to hear that. Thank you.